Welcome to this unit called Fluid Mechanics for Mechanical Engineering. Let's look at dimensional analysis. Unit deals with dimensional analysis, model and similitude, and application of dimensionless parameters. Many important engineering problems cannot be solved completely by theoretical or mathematical methods. Problems of these types are especially common in fluid flow, heat flow, and divisional operations. One method of attacking a problem for which no mathematical equation can be derived is that of empirical experimentation. Let's look at the concepts. Dimensional analysis drastically simplifies the task of feeding experimental data to design equations where a completely mathematical treatment is not possible. It is also useful in checking the consistency of the units in equation, in converting units, and in the scale up of data obtained in physical model to predict the performance of full-scale model. The method is based on the concept of dimension and the use of dimensionless formulas. Dimension analysis does not yield a numerical equation, and experiment is required to complete the solution of the problem. The result of dimensional analysis is valuable in pointing a way to correlation of experimental data suitable for engineering use. Let's look at methods of dimensional analysis. If the number of variables involved in a physical phenomenon are known, then the relation among the variables can be determined by the following two methods. We have Relay's method and Buckingham's pi theorem. Relay methods or relay method. This method is used for determining the expression for a variable which depends upon maximum 3 or 4 variables only. If the number of independent variables become more than 4, then it is very difficult to find the expression for the dependent variable. That is Relay's method. What about Buckingham's pi theorem? If there are n variables, that is independent and dependent variable, in a physical phenomenon, and if these variables contain m fundamental dimensions, that's MLT, then the variables are arranged into n minus m dimensionless number. Each term is called Buckingham's pi theorem. Let's look at applications of the two methods of dimensionless theories. It is used to justify the dependency of one variable with the other. Usually this type of situation occurs in structures and hydraulic machines. To solve this problem efficiently, an excellent tool is identified called dimensionless analysis. These are some of the dimensions used in fluid mechanics when solving equations in fluid mechanics. You have geometrical, that is angle, length, area, volume, first moment of area, second moment of area, strain. So angle, you can either calculate it is in form of arc, radius, or ratio. So the symbol is MLT. We have taught here 0 raised to power 0, and then this one is raised to power 0. Then length, it indicates all linear measurements. So the symbols of length is L. And then area, length times length, that is area, you get L square. And then volume, area times length, you get volume, that is the symbol for volume, that is L cubed. First moment of area, area times length, you get L square. Second moment of area, area times length square, you see there is this square here, so that is L raised to power 4. Strain, extensional stroke length, that is L raised to power 0. Let's look at, we have the kinematic, those are the time, velocity, linear, and then we have pressure, intensity, we have stress, elasticity modules, we have impulse, mass, moment of inertia, we have momentum linear equations, we have momentum angular equations, we have work, energy, power, moment of force, we have viscosity dynamic, viscosity kinematics, we have kinematic, and then we have acceleration linear, we have velocity angular, we have, and then here we have dynamics. These are mass, force, weight, mass density, specific weight, specific gravity. So these are the dimensions and the units that are used when calculating, when you want to calculate these equations in either in Reynolds number or using Reynolds methods or packing up pi theorem. Use this. Mostly you will be interacting with these things when you want to. You will be saying that this is a formula, this one you will be using mostly this one. These equations are the one you will be using more. Let's look at similitude, types of similarities. What is similitude? Similitude is defined as the similarity between the models and its prototype in every respect, which means that the model and prototype are completely similar. Three types of similarities must exist between the model and prototype for you to calculate an equation. Let's look at concepts used in similarities or similitudes. Whenever it is necessary to perform test on a model to obtain information that cannot be obtained by analytical means alone, the rules of similitude must be applied. Similitude is a theory and art of predicting prototype performance from model observations. Let's look at geometrical similarity. Refers to a linear dimension, that is geometrical similarity. Two vessels of different size are geometrically similar if the ratio of the corresponding dimensions on the two scales are the same. If a photographer of two vessels are completely superimposable, they are geometrically similar. Kinematic similarity. This refers to motion and requires geometric similarity and the same ratio of velocities for the corresponding position in the vessel. Dynamic similarity refers to the concerns forces and require all forces ratio for corresponding position to the equal in kinematic similarity vessels. We shall be looking in our next presentation, we shall be looking at the significances of this concept. We shall look at the Euler number, Froude number, and so on. And we shall tackle some questions concerning this dimensional analysis and the applications of dimensional analysis. Thank you for listening my presentation. Let's meet at the next presentation. Thank you.